Almost everyone's seen a Coke and Mentos geyser. Nearly as iconic as the vinegar and baking soda volcano, adding a pack of Mentos to a bottle of soda results in a fountain that never gets old. But why does mixing your favorite soda with breath mints cause such a reaction? Soda is filled with tiny bubbles of CO2, which gives it the signature bubbly taste. When Mentos are added, there is a rapid shift of CO2 from aqueous to gaseous form, forming the bubbles of the geyser. The speed of this reaction is due to the surface properties of the Mentos. Mentos are covered in tiny pores. The pores break up the surface tension of the liquid, allowing CO2 to rapidly congregate into large bubbles. If enough bubbles form fast enough, sufficient pressure will be generated to force themselves out of the top of the bottle, creating the classic Coke and Mentos geyser. Surface tension plays a large role in both the speed of the reaction and the height of the geyser. The higher the surface tension, the slower the reaction, and the smaller the height. The lower the surface tension, the faster the reaction and the greater the height. The more stuff in the liquid, like sugar or aspartame, the lower the surface tension. This is why soda creates a higher geyser than seltzer. The geyser and the reaction can be modeled by the Bernoulli equation. Derived by Leonhard Euler, it states that, for an incompressible flow, the sum of all energy in a streamline is constant for all points along the streamline. This means we can set up the Bernoulli equation for 2 points in the geyser and simplify. Just inside the bottle and at the top of the spray, velocities are 0. P2 represents atmospheric pressure, a constant, so using a manometer, we can find values for the change in pressure, P1 minus P2. Using measured values for pressure and density, we can estimate the height of the geyser. Using these values for rho, h1, and delta p, we find that h2 equals 0.7 meters. While this error may be high due to approximations, simplifications, and measurement error, Bernoulli's equation remains an effective tool to estimate properties of an incompressible fluid. Can you think of other ways to apply Bernoulli's equation to everyday life?